Given, 2 strings word1 and word2 of lowercase English letters. Your task, turn word1 into word2 using insert, delete, or replace, 1 character per step. Output, the minimum number of operations. Example 1, horse to rose. Replace H with R to get rose. Delete the middle R to get rose. Delete E to get rose, which matches the target. That is 3 operations, so the answer is 3. Example 2, intention to execution needs 5 edits. A dynamic program over both prefixes counts every insert, delete, and replace choice and keeps the minimum cost. When you are tasked with transforming one string into another using the fewest edits possible, your brain wants to try everything at once. If you build a naive algorithm that simulates every choice, inserting, deleting, and replacing characters blindly, your decision tree explodes exponentially. It spins out millions of identical, redundant subproblems, completely freezing your program. We need a way to cache our past editing history so we never calculate the same transformation twice. Our massive tactical shift is to build a 2-dimensional grid ledger. The vertical axis represents the prefixes of our source word, and the horizontal axis represents the prefixes of our target word. Every single cell inside this matrix represents a distinct milestone, the absolute minimum number of edits required to convert a specific prefix chunk of word 1 into a specific prefix chunk of word 2. By solving the matrix from top left to bottom right, we turn a terrifying recursive guessing game into a predictable step-by-step puzzle. Before we handle complex words, we establish our baselines. What does it cost to transform an empty string into a 3-character word like rose? It costs exactly 3 insertions. What does it cost to transform a 5-character word like horse into an empty string? It costs exactly 5 deletions. This fills our outer border with a simple counting sequence, providing the foundational gravity that anchors the rest of our calculations. Here is the core magic of dynamic programming: every unsolved cell looks at its immediate neighbors to calculate its next move. Each neighboring cell represents an explicit editing choice. The cell directly above carries the insert cost, the same idea as the top row baseline. The cell to our left carries the delete cost, the same idea as the left column baseline. The cell diagonally behind us represents the cost if we replace a character. To solve the current square, we simply look at these 3 historical costs, find the cheapest one, and add 1 for the operation we just performed. But look at the beautiful exception. What happens when our row and column characters match perfectly, like matching the letter O from both words? If the letters are identical, we don't need to perform any editing operation at all. The cost doesn't increase. The current cell safely ignores its left and top neighbors and inherits the exact value from its diagonal ancestor for free. We skip the edit tax entirely. With our rules established, our algorithm sweeps across the board like a printer head. It computes every optimal subproblem state in a single orderly pass. By the time our cursor conquers the absolute bottom right corner of our matrix, every single cross combination has been evaluated. We read the golden number waiting in that final cell, and we instantly unlock the absolute minimum edit distance in flawless linear matrix time. To execute our solution, we begin by setting up our 2D data matrix, which we'll call DP. We size it with 1 extra row and 1 extra column to account for the empty string prefixes. This grid serves as our progressive decision ledger, where every cell will store the precise minimum cost to transform a slice of our first word into a slice of our second. Next, we establish our base cases by filling out our outer borders. We run 2 quick loops to initialize the first row and column. This represents the raw cost of dealing with an empty string. Converting an empty string to a target prefix requires matching index insertions, and converting a source prefix to an empty string requires matching index deletions. Our boundaries are locked. Now our nested loops begin traversing the inner grid from top left to bottom right. At every single cell, we check if the characters in our strings match. Remember, because our grid uses one-based indexing due to the empty string cushion, we look back at our string characters using our -1 and C-1. Because both characters are an O, no edit is required. We execute our first critical logic path, we inherit the exact value from our diagonal neighbor for free. When the characters do not match, we hit our second logic path. The algorithm stops and polls its immediate neighbors to evaluate its three core choices: replacement from the diagonal, deletion from above, or insertion from the left. We run a minimum value sweep across all three historical neighbors, pick the absolute cheapest editing path, and add a penalty of 1 to account for the operation we just performed. Our nested loops process every subproblem combination seamlessly. As the final cell computes, it aggregates the global minimum sequence of operations. We reach the absolute bottom right corner of our matrix, harvest the final integer waiting there, and instantly return it as our completed solution. One last space optimization: collapse the full table into a single rolling row. Each new row only reads the row above it, so we never need the full table in memory. We keep one array of length n+1 and overwrite it for every row of word 1. A previous variable stores the old diagonal before each cell is updated. That compresses auxiliary space from order m times n down to order n. Let m and n be the lengths of the two strings. Time is O of m times n because every cell is still computed once. Space is O of n with one rolling row. Previous captures the diagonal while we overwrite the array left to right. Two-dimensional version: build an m+1 by n+1 integer table, seed the first row and column with insertion and deletion costs, then fill each cell from its diagonal, top, and left neighbors. One-dimensional version: keep one array of length n+1. After seeding the base row, overwrite it for each row of word 1, with previous storing the old diagonal before each cell update.